Good afternoon, everyone. This is Shudawi presenting, and the work is done by Professor Horiyama and Professor Uehara and me. So, we are going to introduction of our paper. We will talk in 5 parts. First is the introduction, and then is our contribution, and then is the open problem. First, our problem comes from 2 notions. One is the notion of polyomino. A polyomino is a simply connected set of squares. And another notion is a reptile. Reptile is a polygon that can be divided into k replicas, that each of these replicas are similar to the original one. So these 2 notions are proposed by mathematician and engineer and Professor Solomon W. Golomb. Inspired from these 2 notions, we have a naturally common question. Can we combine these 2 and make a new notion that is there any polynomial that it can fall into a cube? Also, it can be divided into small pieces, that each of these small pieces can also fall to a smaller cube. To answer this question, we have a new notion of rep cube. A rep cube is a polyomino that can fall into a cube, and it can be divided into some small polynomials, that each of them can fall to a smaller cube. Moreover, if those small polynomials have the same size, we call them the regular rep cube order k. As you see in the slide, we can divide a big net of cube into some small part, and each of the small part can fall to a smaller cube. For now, the theorem we know about the cube is there exists a pattern of the order k of the regular cube if k equals to these numbers. Also, we know that there exists a regular rep cube of order k, that k equals to 36 times gk squared for any positive integer k prime, and the integer g equals to these numbers. In the slide is some examples of the rep cubes. For example, this is a rep cube of order 2. You can see it can be divided into 2 parts, and each of these parts is a net of a cube. We can fold into a net of root 2. Something like this. Its length is root 2. So this is something like k equals to 4, k equals 5, k equals 8, and k equals 9. Also, we can note there's infinitely many regular rep cubes. The number can keep growing and it will never stop. As we know, there exists a regular rep cube of order 2 and order 4. How about order 3? In the paper, we proved there doesn't exist a regular rep cube of order 3. But how about we assume they exist? If there exists a regular rep cube of order 3 of p, we can assume it can fall into a big cube of q. That p can divide into p1, p2, p3. Each pi can fall into a smaller cube, qi for the L side. Then the large cube of q has the length size of root 3. By the lemma, we have known that if a q can be unfolded to the length size, then every endpoint of the q must be on the grid point of the grid size L. Any endpoint of the root 3 L edge size cannot put on the grid point on the grid of size L. This is a graph, as you can see. There's no endpoint of root 3. So this is the proof. And then we come to the enumeration of rep cubes of order 2 and 4. We assume Si is the polynomials of 6 times I polynomials. And its element Pi can cover a part of the cube of size root k by root k by root k. And it's composed by I nets of a unit cube. We can do the algorithm in this loop. We start from Si equals 1. That S1 is nets of unit cube. then we can compute Si minus 1 and to Si by add P1 to the Pi minus 1. We keep this loop until I equals to k of the order that Sk contains all regular web cubes of order k. This is the simplest case of k equals to 1. When k equals to 1, a regular web cube of order 1 is simply a net of unit cube. As we know, there are all 11 nets of unit cube, so this S1 equals to 11. And later, when k is larger than 1, the algorithm runs in a loop like this. We pick up Pi minus 1 from Si minus 1. For example, this is Pi minus 1. And we attach a P1 to Pi minus 1. Then we make Pi. We test whether Pi can fall into the cube of root k by root k by root k. If it can, we store it into Si. We keep this loop again and again and again. When at last I equals to k, we just output Sk. So as the result, we find there exists 33 in total regular web cube of order 2. As you can see, this is total ones on the slide. And what's special is on the left side. These regular web cube of order 2 are composed of two same pieces. We call these special regular web cubes as uniform web cubes. For the order 2, there are 17 in total. And the red part is just a normal regular web cube. They are composed with different pieces. This is order 2, and how about order 4? We find as a result in order 4 there exists 7,185 regular web cubes of order 4. Among those 7,000 regular web cubes, there are 158 uniform regular web cube of order 4. As you can see in the slide, this is a uniform web cube of order 4, and this is a normal regular web cube. Since we have already found there exists about 158 uniform web cubes, we have a list of the basic shapes that made these uniform web cubes. On the left side, you can see there's a special case that makes 98 of the uniform web cube of order 4. This is most of them. And some patterns like this one, and this one, they cannot make any uniform web cubes. This may be a future topic. So this is the second part of the enumeration of the web cubes. And the third part is the web cube based on the Pythagorean triples. The original problem is there a web cube of order 2 that can fall into a cube of C by C by C? And also it can be divided into two boxes of one A by A and B. So something like this, that A, B, C is the Pythagorean triples. We give a partial answer to this problem. So you can construct a set A, B, C that it can be divided into 5 polyominoes, that each of these can fall into a cube of C by C by C. For example, C equals to 5, and you can divide it into a small cube of 3 by 3 by 3, and with a further divide, it can be reunited into a cube of 4 by 4 by 4. This is the idea. First, we open one of the vertices of a small cube, just like this is 3 by 3 by 3, and we make an opening to the uniform. Make it like a pyramid shape. We attach these two pyramids to a cube of 5 by 5 by 5 on the opposite vertices. For example, like this. Then we twist these two pyramids to make its edge appears to be the edge of C. Something like this. Then we just adjust the overlap part. And this is a bigger picture. You can see. We open the vertices and we attach it on the opposite vertices. We twist that pyramid into a shape like this. Twist. For a clear view, you can see this is two results. One is the triple of 3, 4, 5 triple, and another triple is the 5, 12, and 13 triple. This is an animation for showing how it folds. The bigger one folds into a cube of 5 by 5 by 5. The red one is 3 by 3 by 3. And that small piece combined into a new cube of 4 by 4 by 4. Something like this. Thanks to mechanicity. So this is our contributions. We first prove there's no existence of the regular Rub cube of order 3. Then we make an enumeration of the Rub cubes of order 2 and 4. Then last, we give a partial answer to the Rub cubes of Pythagorean triples. Then here comes open problems. Since we have proved there's no existence of regular Rub cube of 3, and there exists so many Rub cubes, we want to find if there exists a pattern of order k that showing whether there exists a Rub cube or there doesn't exist Rub cube, or it can help us determine whether there is a Rub cube. Another open problem is those special Rub cubes. Since we have already known there exists something like uniform Rub cubes which composed with the same pieces. Also, we have known there exists different patterns that make the same shape, just like this one. The detours are the same, but their patterns are different of this piece. And this one, see, because we don't know how to call it. Also, we want to find if there is something like this one. A Rub cube that consists all those 11 shapes of infinite cube. This is 11 shapes of infinite cube. In the Rub cube of order 50, there exists all of these. This can also be our future problem. Thank you.
You had of the order attributes, you had a diagram showing like 11 on one side and a separation between two types of, that only have one type of development. You had some of them boxed, and I was not sure why they were boxed.
Which?
Back like 5 slides. You have four on the left that are boxed.
These 4 labs are more special because they are central symmetric. But you can regard just like some small priority. So now this is only for the order 2. I'm not sure whether it can be expanded or not. Maybe you can find it in some future bigger Rub cube of maybe in the future. Yes. The numbers. Yes, this one is the number of the amount of the pi. if the PI PI may extend something like this, you have a summit and you have a smaller result. Yes. Yes. So we. Uh, 64 is maybe too big for me. I didn't go that far. Yes. We didn't use that much computer power. So just for now, it's only 2 and 4 for some smaller case. Yes.
One more question? In that case, thank the speaker again.